case B, for our behavior as r goes to infinity, then the behavior of the wave function out here is actually a little bit simpler for us to come by. And the reason is this. Firstly, if we just look at the type of potential that we are looking at, as r goes out to infinity, our potential vanishes, right? And it just goes to zero. So I'm really dealing in a region where, as r goes out to infinity, where the potential is constant. And we already know, we've dealt with this so many times for bound states, how to handle a forbidden region where the potential is constant. I know I must have functions that are just simply exponentially decaying. So in the second region then, I know then that my function that solves this Schrödinger equation, rho of r, must be some exponentially decaying type function, e to the minus alpha r, where alpha equals, and we've done this, right, many times for piecewise constant potentials. Alpha, the exponential constant that we're looking for, always went like square root of, if we wrote it out in its full form, it was twice m over h bar squared times then the potential minus the energy, because we were looking at forbidden regions. Now, in this case, m over h bar squared, that has the numerical value of 1. It's actually 1 over my h bar squared on m constant. So that's 1 over 1 unit energy unit length squared. But it has a numerical value of 1, so I can eliminate it. Also, as r goes to infinity, the effective potential, that's really the potential I'm dealing with here, but the potential and the effective potential actually both go to 0. So therefore, I learned that my alpha constant is the square root of minus 2 e in my dimensionless units. The final thing I'd like to note for you all is that when we were solving for piecewise constant potentials, you might remember that we usually would get these transcendental equations for our k's and our alphas. And then only at the end would we convert our k or alpha into an energy. And we're going to end up with that same type of a thing here. So the plan is we're actually going to solve for the alpha, but then once we know the alpha, once we have alpha, once we find the allowed alphas, it's a quick conversion to get to the allowed energies. The energy then would just be alpha squared over minus 2, or minus 1/2 alpha squared. So if I write down the energy in that form, then rho, as r becomes large, we've learned then we'll have the behavior of some normalization times e to this minus alpha r. And this then tells you the second piece of our asymptotic analysis. And looking at this, I'd like to make one final comment before we move on to the next lecture, where we will actually be using these asymptotic forms. I'd like you to note that the energy in our systems are going to be minus 1/2 alpha squared. And what we are really hoping that they turned out to be from our Bohr-Sommerfeld analysis, which is way up here, is minus 1/2 1 over n squared. So I'm really hoping that that's going to be minus 1/2 1 over n squared. So I'll put a little box here. This is just what we're kind of fantasizing for, right? And that will work. So the big question is, can we show that alpha actually equals 1 over n, where n is an integer, 1, 2, 3, etc. If we are able, in our solution, to finally show and prove this, then in converting us back to regular energies, we will have reproduced the experimental spectrum of the atom, and we will have completely solved the atom. So that's what we are going to take up next time, the use of these asymptotic forms.